Chakravarti, yeah. Manuel is going to probably be speaking for about 30 minutes, more or less, and then we'll open it up for questions. He will be the next full of speakers as well. So I'll do a little intro for you, Manuel. Manuel is a researcher and developer specializing in programming languages. Excuse me. Programming languages and compilers with a focus on functional programming. He has made many contributions to the development of Haskell and Haskell libraries. He co-developed and implemented the foreign function interface and the language extensions for both type families and associated types. He was involved in data, parallel, Haskell, vector, REPA, accelerate. Am I pronouncing all these correctly? Yeah. Development environment. So, without further ado, Mr. Manuel. Haskell for Mac development environment. So, without further ado, Mr. Manuel.
Thank you. Good afternoon. Thank you very much for taking the time to come to PlutusFest and giving us the opportunity to present our work on the Plutus platform. So what I want to do in this talk is I want to answer the question, what is Plutus? And then, moreover, I want to tell you what's special about this. So, well, let's start with the simple. What is Plutus? Well, to summarize in one sentence, Plutus is an platform that develops contract applications on the Cardano blockchain. Now you may say, well, there are other contract platforms. What's so special about Plutus? There are three pillars, three special things about Plutus. The first one is a focus from the ground up on safety and security. The second is for it to work on a superior ledger architecture. And thirdly, we provide an integrated full-stack development environment for the on-chain, off-chain components of contract applications. So let's look at these three in turn, and let's start with safety and security, because that's really at the heart of the matter. As far as safety and security goes, as the website, it won't be secret anymore after today. Maybe you can already guess, it's functional programming. And type. So, yeah, what's this strange stuff else did yesterday? No. So what's so special? Why do we do functional programming? Well, because it's very simple. If you care about safety and security, simplicity is your friend. Functions are just mappings from inputs to outputs. Now you probably think, well, programming has functions, but we've got pure functions, meaning the mapping from inputs to outputs is all the function ever does. It is just entirely characterized by just this mapping. If I use the same function on the same inputs twice, I will get the same result, guaranteed. That's what makes it easy to reason about what the function does. Now, we couple this with types. What's types? Well, it's basically a description of input and output which the function can handle properly. Basically, it tells you, if you use the function in a particular context where it gets those inputs, it's guaranteed to do the right thing. It's going to use something that also certain properties, which is represented in the output type. So the types give us more information about the behavior of the functions. So simplicity. That's it. Phil told you this morning, one way for us to make sure that our work on Plutus is going to be of life is use something established, something based on research from 40, 20 years ago, which has been validated over and over and over again. Well, the notion of pure is either. It's being validated, it's the basis for all of formal scientific reasoning. So it's a good foundation if you want to make sure things actually work. So we get the ability to reason locally. If you look at one pure function, just by itself, you can understand everything about it. You don't have to look at the 50 other models of your program. And then you understand what the thing does. Secondly, we can perform type-directed design, meaning types are not just a way to check whether a function is used in the right context. We use types to actually design our programs. It's a methodology for us to arrive in a constructive manner at a program which is already doing what we want it to do, or is very close. Instead of putting something together and then testing it until maybe eventually works. And finally, and that's also very important, it allows advanced validation, testing techniques, and even form verification. The kind of thing James Chapman has explained in the academic stream before lunch, where we fully formalize the semantics of the Plutus core intermediate language. By taking these two things, we get two major benefits. We achieve an increased understanding of the behavior and of the code we are putting on the blockchain. And secondly, it gives us the tools to find exploits in that code. Discipline of developing the Plutus platform. And let me give an example, one which has been mentioned before, of the outcome is Plutus core. The Plutus core is a representation of programs as we store them on the blockchain. And as Phil has explained, we use this Plutus core based on this omega. Doesn't matter what it exactly means. What's important to know, it's an established calculus which has been validated by the scientific community. Based on this, and small, well-understood system, it's purely function system. Everything in it is just pure function. Everything in it is typed. And by this design approach, we get to a very small Nemo system. So it's different to other virtual machines or similar things you've seen. It's not a code. Everybody byte byte because Bitcoin had bytecode, and Bitcoin had bytecode, and nobody came up with a new idea. Really, copycat. Plutus core is a type functional programming language. A very small one, but it's a full functional programming language. Also, we don't use a virtual machine, a big complex thing which has to validate by something called an abstract machine interpreter, which is based on the operational semantics, very directly on the operational semantics, which we formalize of Plutus core. It's very small. It's what you have on the napkins. It's small, meaning it's a simple system. We can actually, or James, write an actor formalization of it and prove that it's what it's supposed to do. Let's get back from the effort of going through this rigorous development methodology. All right, so much for safety and security, but it's used on the chain. So now this is a ledger. What about the ledger? Well, generally speaking, there are two ledger architectures. Probably not you know. There's the so-called UTXO unspent transaction output ledgers. And then there is account-based ledgers like Ethereum. Now, what's the difference between? Well, if you look at it, the structure of the UTXO ledger really a structured data flow graph. It shows us exactly for each transaction what are the inputs, what are the outputs. Like the pure functions, remember? A function is a map input, so the transactions, they're very similar in nature. In contrast, if you look at an account-based ledger, like Ethereum's, then it's really like object-oriented programming. The accounts are objects and the messages to each other. Well, you may think, well, object-oriented programming is cool. Well, was cool. But have you ever tried to write object-oriented in concurrent and distributed manner? No, because otherwise you wouldn't sit here. You would be going crazy somewhere in a closed institution, maybe. It's crazy. I mean, the entire conference is just devoted to even halfway sanely handle this kind of complexity. We want it here. We want to get it right. We want a compositional structure. So, but what about smart contracts, right? So this is Bitcoin, this is Ethereum, not that interesting, not very powerful. Ethereum, yeah, well, you can write any exploit you want. So, can we have both? Can we have the simplicity and gain the power? So let's look at this in a bit more detail. What's the red bits? It has some outputs, the black bits. So inputs could be money in, outputs, money out, but could also be data. And then we can join all transactions together. Well, the money summing game has to be all right, but there's more once scripts are involved. The outputs, they come with what we call validator, and that's just called our case. And the inputs, they come with a redeemer script. Both are little programs. And in order to check whether we can plug the two together, we have to apply a program call. Well, everything is functions for us, right? It's a function call, and the result is either true, so okay, or it's not true, there's an error, and then we say, no, this transaction has to be rejected. That's the model, the simple model you get in Bitcoin. Now, we've extended this slightly, keeping the spirit, the simplicity, and by the outputs, in addition to the validator, we get a data script. So in addition to the code, we have some data which can travel along the Utx graph. And we also access to some further information on the chain so that we can reason about chains of transactions. And then the validation condition is slightly more complicated. This function, the validator, is a same principle, just a little bit more data involved. Now this gets up what we call the extended UTXO model. So it has the same structure, the same simplicity, the same ease of reasoning about it as the original UTXO ledger. But it provides a very specific more extra power, giving us the best of both worlds. So what's at the Firstly, we have the ability of letting data flow along pure value through the transactions and this transaction graph. So we can trade money on the blockchain, which ultimately that's what we want to do with smart contracts. We want to track other information, not just the funds. Secondly, which is similar to in an account-based model, the account provides you some identity, and often you need identity to reason about things using the same and similar. And that's very important for more complex contracts, we get the ability to write scripts which ensure certain invariants, that certain things are true about, for example, your money not yours, or of chain asset being tracked correctly across multiple transactions, so an entire chain of transactions. That's the power we gain. All right, so that's 2 of 3. So what's the whole full stack business about? Well, what's a smart contract? Let's have a simple crowdfunding example where, well, somebody makes a campaign, other people can pay into this campaign for a certain time until deadline. Then if the funding goal is reached by the deadline, then the campaign owner can get all the paid-in funds out. And if the funding goal doesn't get reached, then of course contributors want to be able to get all the funds back. Campaign owner runs away and doesn't play anymore, then you should also be able to get your funds back. So very simple setup. Let's use that as a little bit of a running example. As Phil mentioned in the beginning, well, if you want to implement this Solidity, then, well, you write some Solidity for Ethereum, and then you write some JavaScript, and then you put the two together. Ad hoc way of constructing a program, but it's necessary because the JavaScript bits, they are associated with the wallet of the user. That's where you spend. This is where all the contract logic happens, and it makes sure that things are only paid out under certain conditions. So you need both. There's no way around it. This is what programming language researchers like myself, we call this 2-level or stage programming models. And this is not a new idea. It's been around for a long time. We have researched this. Some of these ideas go back a long time towards to the first functional programming language, so the list line of languages for the developers. Now, the Solidity on Ethereum, this is very ad hoc. I mean, people have just thrown this together. I don't think they thought about any programming language considerations. So the communication between the two ad hoc is good. No, ad hoc is bad because it's inconvenient. You have to learn 2 languages. That's bad. You can't take code from one language into the other language. No, you have to rewrite it. It's all bad. Between the two, the protocol is quite complicated, and it's difficult to check that the things fit together. So it's fragile. You change one, you still can run it, but it doesn't work properly anymore. You have one, compiler doesn't give you any help. It's a mess. So we thought, well, this is 2-level stage programming. We should be able to do something better with all our programming language up with something better. So our idea was to say, well, for off-chain, let's use Haskell. Yeah. On-chain, also Haskell. Well, actually subset of Haskell, which we call Plutus DX. But now, one nice thing in the area is to learn language. Also, if you have code on-chain, and you need the same data structure off-chain, well, you just use the same definition. If you have code on-chain and you would move it off-chain, just copy paste, don't write into new programming language. That's what you want to do, right? So how do we tie the two together? Well, we use meta programming. Meta programming was first used this. So it's another old proven idea of tying up a 2-level language, which we are using here. So the result is something which is integrated language framework. And it is compact because you don't have to spread things across multiple files, tie them up in an ad hoc way. No, they can all live in one file. Utilize this, of course, if you want to, but there's no need from the programming language. And it's robust because if you mess up the interfaces, the compiler will tell you, oh, you made a mistake. You can run. So you get some information back on what works and what doesn't work. Now, let me give you a slight idea of how this looks like. And I here, I just want to give you an outline of what such a contract looks like. And I'm just going to look at one function, namely, how can I contribute to my project? The function contribute, it gets a campaign as an argument, and how much you want to contribute. Well, then we should check that you actually want to contribute a positive amount. And then this code, this is off-chain code. It's like greenish background. That's off-chain code. So we get your public key from the wallet, from your wallet. Why? Because we have to be able to fund the thing. And then we create a transaction with the script. Well, what do we have to give this function creating the transaction? Well, it has to get the script. I'll talk about this in a second. I have to tell it how much you want to contribute. And then it gets as the data item, remember, extended Utx model, there's a data item, a data script together with the validator. Here we find also. And then we set up a trigger that if a refund condition arises, we can execute the refunding. All right. So now how do we get at this script for validation? Well, that's where it gets interesting. That's where we get the two-level language. And I don't have enough slides, so I'll just continue the next slide. So what we do here, we write more Haskell. And this time we define a validator, which is applied to a particular thing. What is the validator? Now you have some strange symbols, dollars, square brackets. This is just Haskell speak for do some meta programming. And we get blue into the blue part, which is the on-chain code do. Well, first of all, it gets one argument called Tx, which is transaction. And this is syntax for Haskell pattern matching, taking a complex value, splitting its multiple comments. Because to distinguish the transaction to check it's okay, that's our job. We are the validator. And then there are two cases where it's okay. Well, either we are in a refund condition, meaning the all the payments in this transaction go to actually the person who made the contribution, and that person has signed with their correct key this transaction, the signature on the transaction is correct for that person. That's when you get a refund. Or it's time for the campaign owner to collect. In this case, well, we have to be after the campaign deadline, or the inputs have to add up to what the target goal of the campaign was. And finally, of course, we again need the correct signature on the transaction. If two conditions is met, then transaction is good to go. Otherwise, we throw it away. So it's quite compact code. Of course, I appreciate if you hesitate or once you get used to it, it's actually not hard to read. It's just a pure function. All right. So this rounds up the whole three pieces of Plutus, the things which make Plutus special. But let me give you the overall overview. How does this all fit together? Well, you write Plutus code. Then you use the tooling we provide to compile this into a piece of code which communicates with a user's wallet or multiple users. And this provides the wallet with the ability to invoke what we call contract endpoints, the things the user is supposed to use in the contract. In Ethereum. And by doing so, your off-chain contract code will produce transactions, including Plutus core, which go onto the chain. And wallet serves will notify the off-chain code of any events which are interesting to its execution. And this completes the cycle where the off-chain code notifies by an event as the refund trigger we put into place in our example, can submit more transactions, and so on. And that's the overall architecture. It's also quite simple. But simple is good. For simple architectures, we can check that they actually always do the right thing. So overall, that's Plutus. It's from the using with a focus on safety and security, using methods of functional programming and type systems. It uses this serial structure by in this case extended with the extended UTXO model, and it provides a full stack environment where you can do on and off chain code at the same time in an integrated manner. Thank you much. Is there any questions?
I actually very like Utx Model and Bitcoin because its blockchain is small and it's quite important in these days because we know what happened with Ethereum. When you're adding so much information and additional information to all the outputs, what do you plan to do with the growing blockchain like this? Because each time you're creating new output, you're adding code there and data, and if you're using it like 10 times, that means that you have tens of code in the blockchain. So it looks like a kind of big problem with growing like main layer.
So the setup is exactly the same as the plain UTXO chains. So the important data structure in the UTXO chain is the UTXO set. Well, the U in UTXO, meaning you put all these transactions in there, and all the transaction outputs which have not been spent yet, they need to be in the UTXO set. But the crucial thing is once you spend an output, it cannot be spent again. This is the double spend restriction. At that moment, you can call that output from the UTXO new our extended model. This is the case in Bitcoin already. And so basically, we have a natural form of garbage collection, which if you're programming language, it's like a linear type system. So if you know everything is single use, once it's used, you can throw it away. You don't need complicated reference counting, garbage collection, or anything. It does once it's used. And so the data structure, the main data structure which has to be kept in memory, the UTXO set, grows and shrinks in the exact same manner as it does for coin or Cardano today.
Well, first of all, amazing talk. I really enjoyed it. And we inherit a lot of really cool things about Haskell, but also some of the challenging things, especially I would say adopt the challenge of adoption, right? Strategy that Cardano or the bigger ecosystem is doing for this to be adapted into a critical mass for the environment.
Yeah, the excellent. Thank you very much. So and the outlook is extremely bright. So as I think we've heard this morning, and I've been a while doing training courses, educating developers in the use of Haskell. This is going to continue. So we are actively working in teaching people how to use and extension from now on, also Plutus. That's number one. Number two, if you look at what's happening in the wider developer community at the moment, you will see there's a sea change. So I kind of flippantly refer to object-oriented programming as the thing of the past, because if you read tech magazines these days, they're very critical of fulfill the promises of abstraction, modularity, and so on. And there's a strong shift towards functional programming. And you can see this on a large scale. For example, if you look at the Apple recently, they used to have all the developers write Objective-C. Now they converted everything over to Swift. Swift is a hybrid language, a hybrid functional objective language. But it's very on functional programming, and all the type system things we are doing, they are all present in Swift. The type system Swift is not any simpler or biometric is. So what has done in the last few years, they've taken these millions of developers, like all the iPhone, Mac, and so on developers, and converted them from writing Objective-C, right? So it's not like large chunks of developers aren't able to make this move to functional programming. It's a matter of explaining why, providing the teaching material for people to achieve it. But I don't see this as a significant obstacle, and I think Apple has proven you can do it. And if you generally look at the developer meetups and there's interest in functional programming, more and more people learn functional programming anyway, whether it's in Haskell or any other functional programming language. So what I would say, we are going with exact time in the direction of where everybody else is heading as far as programming languages go, instead of being stuck in the past with object-oriented programming.
Thank you.
There was also a gentleman behind you.
Thank you. I'm not a programmer, but I would like to be sure to understand. So I have two questions. First question is, a program can develop a program or a smart contract with Marlowe and use Plutus for more complex to add some functionality?
So the way it works is that Marlowe can be compiled to Plutus, so it's basically implemented on top of Plutus,
Yeah.
and the two integrate directly as a result. So our modus operandi at the moment is for Marlowe to be a self-contained system where you avoid having to have the developer experience, and the domain expert can approve contract. Due to the integration of Plutus with Marlowe, what you're describing, to use Plutus as a sort of extension language of Marlowe, I think is a plausible way of work. We have gone far because to get to this day, we had to build the systems themselves, but I think it's totally feasible. Or you're using the same infrastructure, namely the Plutus infrastructure, and then a collaboration between Marlowe contracts and Plutus contracts is effectively just two Plutus contracts collaborating.
And second question, do I understand that you can develop separate contract with Plutus?
Yes. Sure.
In the same software, in the same development, like I'm not in Ethereum. You have multiple smart contracts that can interact with an interface.
Mm-hmm.
I understand that with Plutus, you don't have those multiple contracts that you have to connect with.
Okay. So what I'm saying is that the on-chain, off-chain code is integrated, but in one program, you can, and typically, if you look at the examples we will provide in a second. And overall, Plutus contract will contain multiple on-chain bits. That's totally fine. There's no limitation. It's just that I use this color coding with the blue and the green, but there can be many blue things in one big green box. And there's no limitation on how many or anything. It's just, for the simple example, it's always one-on-one, because otherwise that can't be on a slide anymore. We can do one more, yeah.
One last question.
Thank you. I had a quick question. I'm not a software engineer, so forgive me, this question sounds a little ignorant, but you were mentioning Ethereum and how someone who's coding has to do an on-chain and off-chain solutions to code in Solidity and Java. But for Plutus, they just have to know Haskell. And basically my question, is that because like you're using more compilers, or why the solution for off-chain and on-chain with Plutus so much different than Ethereum? Is it does it have to do anything with the compilers, or?
Yeah, it has something to do with the compilers. Basically, what we are doing is an old thing, which my background is very much in research, programming languages, compilers, and these kind of things. And what we like to do, what we compiler writers like to do, we want to make the life of people who write code easy. And in this case, instead of letting people manually use these two different languages and then manually kind of connecting them and handling all the field system format, all basically every single contract developer doing that for themselves, we do it for them. So we have a compiler which is more sophisticated and which performs the separation of the one program into two or multiples, according to your question, and tying the two up and making sure that it all fits together. We automate that. We have developed these things so that the Plutus developer doesn't have to do it manually anymore. So it's a matter of automation through the compiler infrastructure. Does that answer your question?
Yes, it does make sense.
Thank you. I think we have to stop with questions here, because you may be interested to actually see this in real life, and that's what's going to happen next. We will have microphones and presenting Plutus playgrounds.
So I'm going to do a very quick mic swap with you guys.
Quick change.
Is that gonna work?
Ooh, that's sure. Oh wow, that looks great. How's that look? That looks okay. Good.
I'm feeling like a cycle. I'm feeling like an unforced cycle.
Okay. You go up, you go down. All the slack, feel all the slack around.
Oh wait, don't do that. Maybe I should just hold the mic for now.
Possibly.
I mean, because otherwise we have to do this off. I think
The radio mics are good to use, if that's okay. You can hold the handhold. You could hold them.
Maybe I should hold the mic for you when we get to you. Or we'll see.
It's about 20 seconds.
That's true. It's manageable.
You pop that in there.
Yep.
Connected.
Okay. Am I audible? Tap tap tap. Yes. Good. We're good to go.
Hang on.
Test. Hello. 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 Testing, testing, 1, 2, 3. Test, 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 test. It's not on mute. Okay, it's on mute. All right, here we go. So I am very happy to be talking to you here because Jan and I get the envious role of being Father Christmas in this conference, in that we get to actually show you the real deal. You know, so far I've heard lots of people telling you lots of nice things about programming languages and theory and all this stuff. But at this point, maybe it's all vaporware. You don't know. And I'm here to tell you that it is not vaporware. And also to do something extremely dangerous, which is tell you how to actually do something. And more than that, we're actually going to do some of that live in front of you. And to the point at which I'm struck down by the god of demos for my hubris. But let's see how far we get before the lightning strikes. So today, what we're going to talk to you about is Plutus Playground. And the point of the Plutus Playground is, well, why are we here? What is the point of this conference? All of this infrastructure that we're building up. Well, at the end of the day, we want to actually write some smart contracts. We want to do something with this system that we've been building. And Plutus Playground is here to help you. It's an environment for writing and testing smart contracts in your browser. You don't have to install dependencies unless you want to. And so it's a bit like Remix if you in the Ethereum world, if you've seen that. And that's what we're going to be showing you today. And you can go all the way up to actually testing your contracts and seeing that they actually do what you expect them to do and don't just, send all the money to my account. I should really put that in as a backdoor. So first of all, I'm just going to do a little bit of a retread of some of the ground that Manuel has so adeptly covered, just to make sure that we're all on the same page here with what's going on, because this is really the pedal hitting the metal. So we need to know what we're doing. So to revise a little bit, the anatomy of a smart contract. You've heard people say on-chain, off-chain, over and over again. I'm going to say it again. We have some code that runs off the chain. It runs in the user's wallet, typically. This is what they interact with. It's what listens to them saying, I want to send all my money to the Fuzzy Bunny Kittens crowdfunding campaign, and then submits a transaction that actually does. And then there's the on-chain code, which is what actually lives in the transaction. It runs during transaction validation. It makes sure that nobody steals all the money. That's very important. But these two pieces of code, as Manuel has, are very coupled. They need to understand each other. They need to cooperate. They need to exchange data between each other, and they jolly well better do that in the same format. Otherwise, we're going to drop everything on the floor, and everybody's going to be sad and funny. So the goal of the Plutus platform is to bring these things much closer together, so you can write your on-chain code and your off-chain code in the same language, and that language is Haskell, and even in the than that, you can actually really reuse the same types between the two. So you can just, the same data structures, the same definitions, and maybe if you're not a Haskell developer, you don't feel that deep inner feeling of joy in me, but I promise you, this is the thing you want. This is the thing that will make your life easier. The types are definitely your friend, and you want to share them as much as you can. Moreover, the library and support that we have built allows you to write exactly the same code to define a contract and run it on both Cardano, obviously, because that's where the real stuff happens, but also on the Plutus, so on a local emulator, which we affectionately call the mock chain. And that's what's actually powering the Plutus Playground under the scenes. But crucially, you don't have to jump through horrible, awkward hoops to do testing, just the same nice interface. So let's drill a little bit further down into the anatomy of what's going on. So we'll continue our color coding adventure. We have this blob of off-chain code written inside the user's wallet, and then, as Manuel has shown you, you have these fancy, well, the previously blue-colored, now purple-colored blocks that live in those quotation blocks that actually are going to turn into on-chain code. which are also written in Haskell, or as we like to call it, PlutusTX, because it's not quite Haskell, but pretty much Haskell. And these are what actually define the logic of your transaction most of the time. So that's where, as you saw in the crowdfunding campaign, check that you got enough money, check that the deadline is passed, yes, okay, no, not okay. That's where that's happening. And so that's the second stage, the first stage being the Haskell, second stage being the PlutusTX. But in addition to that, we want to make it easy for you to come across these boundaries. You don't want the stages to be awkward, rigid things that you keep butting up against as a programmer. And in particular, you often want to parameterize your contracts. You don't always want to pay Jim 10 ADA. Sometimes you want to pay Jane 10 ADA. You want to actually be able to parameterize them. And so we make it easy for you to lift chunks of data from the Haskell world at runtime in your off-chain code into the on-chain world seamlessly. And so that will all just work. And this is one of these things that hopefully when we actually get to look at it, you might not even notice that it's interesting. That's the goal, is that it should seem really easy, even though there's actually work going on behind the scenes. And then this then all gets turned into a transaction that actually goes on the chain. And we're going to see all of these pieces shortly. I then also want to say a little bit more about what Manuel described earlier, where he explained about the extended UTXO model and how validation works. So just as a reminder, how do we check whether we can spend a transaction output? Well, spend transaction output by taking, and we do that by taking its validator and just feeding it a bunch of bits of information. And if it evaluates successfully, then it's fine. If it doesn't, then the transaction is rejected. And this is done by the validator. And if you don't know what that means, it's the person who actually runs all the code. It's part of the Ouroboros protocol. And the way that works is that, well, we're writing in a functional language. This validator script is just a function. And that's exactly the pattern that we will see literally in the code in a moment. So remember that, that's going to happen. In addition, the Manuel denoted this with a little sigma. There's some additional information about the transaction as well. Things like what block height are we at, i.e. like what time is it, and some other pieces of information. And crucially, this is actually uses exactly the same mechanism for lifting data into on code. You can and you can also then use the same types. So not only can we share our types between our on-chain code and our off-chain code, we can share our types with what happens at validation time with the slot leaders, and we can be sure that everything is just okay, and we don't worry accidentally screwing it all up when we do it ourselves. And so to summarize, there are kind of 4 interactions that we need to remember and bear in mind. Conveniently, corresponding examples for how to import when you're doing this for real. And again, in a moment, you will see precisely these things in action. So the first thing that we need to remember is that the off-chain code talks to the wallet. This is like part B, submit a transaction, register that you want a trigger to take an action on some later date. These are things that the wallet is going to do for you, and you need to say, please do this. And that lives in, surprisingly, the off-chain code also needs to actually make the transactions. That in order to do something, you have to make a transaction so you can submit it onto the blockchain and actually have something happen. And all of this material is handled by the module without on the ledger. Thirdly, we had this staging business whereby we write this PlutusTX code that gets turned into Plutus core code that goes on the blockchain. There's some stuff like that in the PlutusTX module. And finally, there's the types and structures that are used during validation that you will want to care about when you're writing validators, and those live in the validation line. So those are the kind of the four things that are going on that you might care about, and we'll see those in a moment. So I'm now going to actually show you some code in Emacs or else. The font size on this is not ideal. Oh dear. Is it possible to turn this off? If I just take it out of the socket. Nobody saw that. That's fine. So this is a Haskell file. Hooray, Haskell. If you haven't seen Haskell before, this is not going to be a Haskell tutorial, but hopefully it will not be too bewildering. And so there's a little bit of stuff beginning, which we won't worry too much about now. But I suppose can I move this a bit? There we go. We do see that here I have written 4 imports corresponding to the 4 that I just told you about. As a reminder, it's about stage code and writing things that run on the chain. Wallet is about talking to the wallet. Ledger is about making transactions. Validation is about things that happen at validation time. So that's what you do right. But I'm now going to pop the hood a little bit and show you what's really going on here. And the reason I'm going to do this is because although it's unlikely that you're actually going to care about the Plutus core and what's going on, it is interesting to know the sort of a language, what you're doing looks like. It's sort of going to prove to you that there really is something there. You might have no idea what it means, but it exists. I'm not just making this up. It's not, these functions are not implemented. The functions are in fact implemented. They just like string all the time. So here is the simplest example I could come up with of using PlutusTX. So we're going to write the +1 function as a function on the chain, adding it in 1 to an integer. And well, what is that going to look like? Well, it's going to be an opaque blob of code as far as the off-chain code is concerned. The off-chain code is just once you've made it, you can't really do much with it. It's going to get run later. But that's what it looks like. And here we see the funny quotes, the funny dollars and brackets that be old hat. But for the rest of us, let's take a moment to think about what's happening. And what's happening is that between these funny double bar brackets, we have a Haskell program. I'm going to reformat it so that it fits on the screen. It's a function that takes an integer and adds 1 to the integer. Very exciting. These little quote brackets do is give you a representation of that Haskell program, which is what we're then going to compile. So that's all this is. This is just, you can just think of this as the program that's inside then to the PlutusTX.compile function, which surprisingly compiles it. And then finally, we feed it into these double dollars, which takes us back into the world and the quotation world, actually shoves the compiled program into your program to use it. Now, what that actually means is we end up with a Plutus core program. So let's look at it. It's what it needs to do. I know what it needs to do. Rotate it like that. So this is a genuine Plutus core program that you could put on the blockchain. Ooh. And if you're interesting, that's interesting. So this is actually something that we do to make sure that when things change, we know exactly what version of the language is being used, so we don't do the wrong thing. You can see a bunch of incomprehensible nonsense. What there corresponds to the bit that we wrote, and the rest of it is not so interesting at the moment. And if we squint, we can see that this is a lambda function, so like a function, which is going to take some comprehensive name. Promise you this is an integer, and is going to, I promise you this is calling it add integer, add, and this is 1, is going to add 1 to it. So at the end of the day, Plutus core is not that dissimilar from Haskell anyway. And so going on under the hood here is not so clever. There is some cleverness, more cleverness that we'll talk a bit about later, but it's comprehensible. We're just one of the virtues of the taken is that we actually are quite close to how Haskell represents things. So now this would not be terribly useful if we were only able to use integers. I mean, you could use integers, not everything. And in fact, we can just use pretty much all of the Haskell data types that we would want to. So here's a very simple example where we use the type AB, which is in the Haskell prelude and just is either a thing either there or it's there. It's like pattern match it. And in the case that there's something there, it gives you the thing. In the case that there's nothing there, it gives you 0. So it's give me this thing plus 0. And this will just work. Hooray! You can reuse your data type, write your own data types, and things will just work. It's not special built in. It's just whatever you want to write. And I won't show you that because that's a bit longer. What I will show you is here is a ever so slightly more real program. So this is actually part of the example that Jan is going to show you in a second. This is a real validator script for a simple guessing game. And so this has a couple of user-defined data types, a couple of bits of magic to make sure that you can do that lifting that we talked about earlier. And then it's just a function. And well, what do validators look like? Well, they're functions that take a redeemer, the data, the validation info, just like Manuel said, nothing fancy here, it's exactly the same. And then it does some computation and decides whether or not it's going to accept it. And this, it's simple but significantly more complex program is also, what do I call it? Is also, it's very long. It's not that long, but it's quite long for an Emacs terminal. But it's a real program that we can write and that works and that you can actually execute using the Plutus core evaluator for real in the Plutus grounds. It will actually evaluate and do what you want us to do. And I'm now going to hand over to Jan, who's going to show you how to use the things in Anger and actually see something that isn't gibberish. You just want to use the one that's on there. Okay.
We can do that.
Yeah.
Why not? 20 minutes, half an hour.
Yeah,
aren't you?
that's fine.
Might as well.
Right, there you go.
So, thank you. Oh, no. Oh, you had two, didn't you? And if you feed that one down. That's lovely, thank you, sir.
If you want direct questions, feel free to.
So keep going to Slack. That one as well. Put that one down.
No, down.
Yeah, take that. That's fine. Pull those both out. Both ears. Lovely. Doesn't like that, does it? Find your pocket. Just needs a bit of time.
Okay.
You didn't feel that,
Yeah. Okay. Thanks. So this is the Plutus playground. Just live in the web app. So this is actually working, and you can try it out for yourself later. When you open it, you'll see a code editor, and that's the field where we're going to write the smart contract. And it comes preloaded with a number of examples. So we have a training campaign, a game, one example that just produces different log and error messages, and a vesting scheme. And we will look at those in a minute. I just want the interface first. So we have the contract. We click compile. And that brings us to the second part of the playground. And this is where we can set up a simulation on the blockchain that uses this contract. So we can set up a number of wallets, each wallet an initial distribution of funds, so 10 ADA in this case. And these wallets can perform actions. And these actions, they're going to be defined in the contract that we will write. And because we have an empty contract here, there's only one that is pay something to a public key owned by another wallet. Let's try that. Pay 8 to the second wallet. The public key of the wallet in the playground is of the wallet. And then wallet pays back 8 to wallet 1. And we can put up any of actions in the sequence here, and then the emulator will run it against the mock chain. Oops, sorry. So now we get to the third part of the playground, and that's where we see the result graph here. And this graph shows the entire blockchain that has been generated. And the time in this graph flows from top to, so the node at the top, that's the initial transaction, and the other nodes are the remaining transactions, and the node at the bottom here is UTXO nodes and outputs, and all the other nodes are transactions. And the edges in this graph, they're pairs of input-output connections. So one transaction consumes the output of the previous thing. So we can see here, each wallet got 10 ADA initially, and two received 8 ADA from wallet 1, and wallet 1 received 8 ADA from wallet 2. The second of the output is this log that we'll see here, and that's happened on in simulation. So we see transactions that were valid, transactions that were rejected, any script failures, log messages from the wallets, and quite a lot of information from this. And here we see 3 transactions, the initial one, and then the 2 that I just created. Final balances at the end. So each wallet is back to 10 ADA that it started with. So this is the general workflow of the playground. We write something, and we set up the simulation and to make sure that the contract behaved exactly like we wanted it to. Now this is the full source code for this game that we already saw the validator of earlier in Michael's talk. I'm just going to make it a bit bigger. So we start with the module name, and we have the imports that we need as before. So we have PlutusTX, the prelude with some helpful functions, ledger, validation, and wallet import. And when we're working in the play, we also import the contract module, because that lets us define the contract endpoints that the wallets are going to use to create transactions with this endpoint. And then in this line, we have another Haskell that we're in byte string that we only need in this particular contract. So we can use any other, a lot of other Haskell libraries in here as well. Now we need that and puts the hash of that word on the chain. So they're using a transaction output that's locked by the, and to encode the hashed word, we just have this hashed string data type. And for any data type, we want to call on-chain rotation, we need to call PlutusTX.makeLift. That's why we have that here. And then there's a helper function that lets us take a Haskell string and press the transaction. And in this, that's where so first we have the hashed word here using the SHA-2 function, and we embed that into the data script lifted. And lettered or lifted takes anything that you have defined makelift on and puts that into the on-chain representation. We need that for the data script, and then a similar of the other player. And here we have a clear string, which is also going to be the byte string on the chain. And by using these these types that we find, make sure that in the byte script we don't compare two wrong things. So we don't compare a clear string and a what was it called? A clear string and a hash string, but we always compare two hash strings. So we have the clear string. We can construct redeemer scripts containing the clear string with the make redeemer script function. And then this is the validator. This codes the game logic. So we have two quotation marks here and here, line 42, and anything in between that this is the actual on-chain code, all written in Haskell again. And in here, we can use the import from earlier. So because we imported the prelude qualified SP, then we can use any functions that are defined in there with the splicing operator. This is the $2. So that lets us use outside of this script and puts them into the script. So we compare the 2 byte strings. If they match, then we just terminate. We just turn the no error. Then we produce an error using the error function and a little log message so that we know what happened. Now we do chain code. We need to define the contract endpoints now. So how do the wallets interact with the game? And that's what the next few functions here are for. First, the first interaction that we do is lock fund secret word. This is what the first player is going to do. So we have a function that takes 2 arguments, a string and the value, and it returns a value of type mock wallet to interact with the blockchain. So we're using the wallet API as an intermediary to talk to the chain. And pay to script here, that's one of the functions, and was paying the value to the address of the script using our make data script function from above. Now the second endpoint that we need is guess, which takes the guess and also returns the mock wallet function, because here we're using collect from script, which instructs the wallet to take out all the unspent transaction outputs at the script address. There's a little problem with this at the moment, because to collect all the outputs at the script address, the wallet needs to know that this is an interesting address so that it can watch this for any user. Otherwise it doesn't, because it can't just watch all the addresses of the entire chain all the time. And to make the wallet aware that this is an interesting address, with that game, and it just tells the wallet to start watching the game address. At the end of the contract, we have 3 calls to make function, and that's what we'll create the make function lock, make function guess, and start game. And we can call make function on any function that has this structure that returns the mock wallet. And now you can see that the wallets have learned how to do these actions. They can lock something, they can make a guess, and they can start the game. 2 have start the game. Wallet 1 will lock the funds, and then wallet 2 will make a guess. Let's see how that works. Let's click evaluate. Okay, so we have the 1 locking the 8 ADA, and then this is wallet 2 retrieving them because the guess was correct. And that little bit here, that's the change that goes back to wallet 1. And in the there were test as you would expect, and wallet 2 ends up with 18 ADA. Now there's no transaction that spends this output. And we can see in the log that the validation failed for this, and detailed reasons why validation failed. You won't get that on the real chain, but it's very useful for designing and debugging contract. Wallet gets 10 ADA, wallet 1, 2 ADA, and the remaining 8 ADA that are missing, they're still locked in the script output. Let's look at the funding contract now. I just want to show you the blockchain in a little bit more detail that Manuel mentioned earlier. So we've this is the contract endpoint that makes the contribution to the company, and we've made we register this refund trigger, and that's a condition on the blockchain that becomes true at some point. So in this case, it means the campaign the deadline campaign has passed. and fund it. So in that case, the contributor is entitled to a refund. When that happens, it calls the refund handler. So this is like an event-based system where you have some conditions, and then you can call an handler that reacts to this condition. In this case, the refund handler and the guessing endpoint that we had in the game earlier. Because earlier we were tried to reclaim all of the contributions to the address, but only the one that we made ourselves in the initial transaction. And that's why we're calling from and only claim back our own contribution. If we try to collect all the other ones, then the transaction would be invalid, and we wouldn't get anything back. So we make sure to create a transaction. This whole blockchain trigger system that all runs in the client code, so it doesn't go on the chain. This is done by the wallets themselves. So we're going to run a little campaign, 2 contributors, and one is the campaign owner, and they have to call scale action again, so that they're watching the address. And zoom out. And you can see here that it generates the correct form for the data types that you want. So we have campaign data, and the playground automatically gives us these inputs here to put in the blockchain height, values, and anything that we need. So let's say the campaign's target 15 ADA, collection deadline 20, and the owner of the campaign is this public key. Let's make 2 contributions. And we have to make sure to put in exactly the same details, because the campaign, this definition is part of the address of the script, and if we put in a that is part of the campaign. So 15, 20, owner is 1, and then let's contribute 8. And now we have to get 10 blocks. So the campaign owner won't even attempt to collect the funds yet. So we can use this button here, add wait action, to add a number of empty blocks to the chain. Just to delay time. Now this is a bit more complex, but you can see these are the 2 contributions now, and this is collecting. And now if you look at the logs, we also see these messages from the wallets. So in the wallet app, you can also log information. And then at wallet, at block height 10, this is when the collect funds trigger fired and collected the 2 contributions. And happens a successful campaign. Say wallet 3 only contributes 2 ADA. And we have to add some more blocks. So we have to get past the campaign collection deadline. 20 blocks. Now you can see that the contributions here were claimed by the contributor. Message from wallet 2 claiming refund, message from wallet 3 claiming refund, and everybody's back to the balance that they started with. So we can use the playground to go through really complex interactions with our contracts, and it all considering this, because when you click evaluate, it really spins all the wheels. It compiles the contract, emulates the transactions, it runs the code to the web interface. That's all I wanted to show for the demo. There's some links here to more documentation. The URL of the playground is here. you can try out these yourselves. And there's a Docker image as well if you want to download it and run it locally. And I encourage you to try it out, make some changes, see how the contracts behave. Thank you.
So, well, I'm completely amazed by what you goes on. It's really cool. In Ethereum, well, going back here, I'm really amazed. So in Ethereum, there's oracles, right, to access this outside world, multiple side effectful, ugly information. And there's an issue with, in these data sources. Is there any similar solution to inputting, third-party parameters in or
in some of the sample contracts that we have in the GitHub repository, there are trusted oracles. So we have defined a data type for trusted oracles with a known public key, and then taking data. And for the untrusted case, and that's still an open question. So.
Thanks.
So I had a practical question with regards to Plutus Playground, which is, do you have any way more to plan potentially adversarial actions? So one thing that I was thinking in the case of the crowdfunding campaign is, for example, if the organizer does not claim their funds, that's something you can simulate? And if so, how?
Yeah, we can comment out the claim funds. So outside of the playground. Sorry. It's something new to the playground, and in there we have more detailed, a more detailed simulation of which transactions the wallets are aware of. So in there you could simulate that the owner has a network, something does not know that all the funds are there and fails to collect them, and then the contributors will still be able to do.
They decide not to validate your transactions and so on. And I think we're hoping to eventually hook these up so we're doing sort of property-based testing, and we can generate arbitrary different series. You can check that certain properties hold even if the network goes out in the most awkward possible place.
All right, thank you.
Anyone else?
Well, it's a really simple question. Is you leave me a data type from Haskell into the Plutus?
More or less. I mean, if none of it has functions inside it, basically. It'll work for most data-like things. There's a bit more documentation on precisely. Well, there needs to be a bit more documentation on precisely what the limitations are, but anything parameters of this crowdfunding campaign, all that is going to be fine. But if you want to pass in coordinator of something, then maybe not.
So basically, just break types, which just integers and strings combined together, and that's it.
Or other types which you can lift, so the stuff should all compose appropriately.
You can have lists, trees, you can have fancy parameterized data types. Some products, basically any polynomial function would count, I guess. Sorry, powerful, so maybe one day, but maybe not. It's theoretically it's possible to import the HC core
guys. How are you? So, regarding the Ethereum smart contract system has lost $5 billion due to mail.
Here's probably just what my mom said earlier, that you already gain a bunch of stuff by architecting the system in the way that we have done, whereby you're doing things in language, you can leverage Haskell's type system, both to have the compiler stop you from doing really stupid things, but also to design better programs and make your legal states unrepresentable and all of that stuff that we like to talk about. Because we have all this type information and because we're working with Haskell, there's a lot more possibility to add on additional. Yeah, so like we could potentially use things like liquid Haskell or something. So there's we have a lot of avenues open toward.
So it must be sure that the contract system is more secure and less prone to mistakes by the humans, because you're making something for humans to use it.
For sure, and I think that what we're doing is going to be easier and harder to make mistakes. Matt, what do you want to do? Look what you want to say.
So that's it. This is why we are taking this approach. If you look at recent research and find that a lot of the recent success stories, functional programming has been quite central, and this is because just from a human's ability, a programmer's ability to read about how without full support and without any theorem provers, and then if you really mean it, there's really a lot of money at stake, then you can throw more heavyweight machinery at it and automatic tools you can use go down to full formal verification. And this has been demonstrated multiple times now with languages like Haskell, where the compiler catches no errors, to full formal verifications, all open. And it depends on how much you want to spend to validate your smart contract, and that depends on how much smart contract, and that depends on how much value is locked up in.
Okay, before I start, I'm not technical in the very least. We want on a base protocol. We're looking for a base protocol that meets our requirements. So, of course, we're looking at the Ethereum and specifically machine-to-machine interaction. And so, I've been keeping a close eye on the evolution of DAOs, distributed autonomous organizations. And it just seems inevitable to me that the financial sector, a lot of the trades are being done in the blink of an eye using AI algorithm humans that continue to make mistakes through to careless programming. So is that something you guys are thinking about at all, or is it entirely a human-machine interface? This program, or do you see AIs being able to actually program repeatable? I don't think in complex environments, but things that are very easily repeatable. It's
a computer. So if you write, so Jan has an example that's like this futures contract. You can write, you can have your program call the function that submits a transaction to buy a future at price. The transaction, that's because it's parameterized. Like the computer doesn't need to write the futures contract for you, and that's the set. And I think as I understand it, that's the sense in which a lot of trading that happens in financial is automated. More, you want to make lots of quick trades, but of a similar type. I'm not sure whether I don't think we're particularly looking towards computers writing Dino contracts. But these contracts, even parameterized contracts,
and very repeatable, I would imagine.
Once you parameterize it, that actually probably gives you most of the flexibility that you want in a lot of cases. But we'd probably need examples to really decide this.
Yeah, we can continue the conversation offline.
All right, that was the last question.
All right, thank you very much, guys. Last but not least, Haskell wizard himself, Duncan Coots. You all know Duncan. Duncan is a computer scientist and a Haskell consultant and community member. He holds computer science. I feel like this is like, anyway, so wrestling. He holds a PhD in computer science and has been using Haskell for nearly 20 years. He is founding partner of Well-Typed Consultancy. He spent a decade helping customers build applications in Haskell and making improvements to the language. He started working with us, IOHK, in 2016, is the head of engineering and chief technical architect.
You did it.
Oh, is that right?
That's how you do that. I'm just kidding.
Thanks very much. It's about slightly the wider context of assurance within Cardano. I mean, we've heard a lot today about the importance of building stuff that works, and I want to talk about the same topic slightly, not Plutus and Marlowe specifically. So yeah, my talk is show me the evidence, because it's all about evidence-based approaches to making sure that after what we do. So this is a very difficult space. The challenges in the cryptocurrency space are legion. There are so many ways that we can fail, and not just the obvious one. I mean, we flawed physical design. Aglos is here to make sure that we don't do that. But that's one way to fail. You can have an incorrect implementation of a design like Ouroboros. It's easy. Those kinds of the typical software mistakes that occur throughout history. I don't mean crypto space, I mean just the kind of programming mistakes that amateur cryptography failure. That's another way to fail. It's very easy to fail that way. I like to say that amateur cryptography is like amateur brain surgery. It's not something you should engage in. You can fail in this space by missing performance deadlines. The Ouroboros protocol has real-time performance constraints, real-time timing constraints. They're more than microseconds, but nevertheless there are deadlines. The systems can fail by collapsing under load. When lots of people try to use it and hit the maximum capacity of the system can fall over. It's very easy to write systems that do that. There's a failure to scale. If we look at Ethereum, it works. We can argue about the details, but broadly speaking, it works. But as soon as CryptoKitties took over, then it could not scale to the capacity that people wanted to use it for. So that's a way a system could fail or can fail, is by just failing to scale to meet the needs, the capacity needs of all the users. And then there's denial of service, not just and then there's other more esoteric things, but nevertheless things that could cause could be costs that are borne by the people running the system are not properly compensated by fees. Bother to run the system, I'm losing money doing so, and then the system can fail. That's a very interesting one. Bitcoin has a major problem there with like size of the bigger compensation for it. So there's interesting economic attacks on these systems. Then you can have a social or voting collapse. This is why we do governance research. The system can fail to make progress because mechanism is helpful to agree. And then macroeconomics. I mean, the list goes on and on and on. And you need all of these problems, that are soluble, but they all need different specialities. It's like one area or software. You need experts in all these different areas. It's a highly multidisciplinary space. So that's what makes this space really interesting and really challenging, and very hard. And the sad thing is that the software industry as a whole, the quality is not what the reputation is for in the software industry. I think when was the last time you had a software update on your phone or your laptop or something, to fix some critical bug in Patch Tuesday or whatever. We get these patches all the time because those are flaws in the software that was already deployed, and that's actually the stuff that's of relatively high quality, where they bother to patch these things. Most random maps that you're using or other bits of software behind the scenes that you never see are full of problems all over the place. And just the other day, the O2 network went down. These kinds of things are
all over the place. We see them. So normal industry standard software, which is what we deal with interact with most of the time, is not great. If I was in a less illustrious company, I would say something ruder about industry standard. I consider industry standard to be a badge of shame and not a badge of pride. So industry standard software is not high assurance. We don't have any assurance that it does what we think it does. It's not terrible bugs. And if you follow industry standard software development practices, you get industry standard results. We do the same thing, and this should not surprise us. And doing the same thing over and over and hoping that next time it's better in a different can happen. And this is a real problem for the cryptocurrency space, because you can't do Patch Tuesday in the cryptocurrency space, because they will steal the money before next Tuesday. Before you have had to find the solution, write the patch, and deploy it, then and someone at the back was saying, $5 billion overall has been lost on Ethereum smart contracts that were written back. They will steal it. So assurance on quality in the cryptocurrency space is even more important than it is with your mobile phone network working, perhaps. I think, well, if or it's not working, but here there's lots of money at stake. Or if we believe that it's real money, then we ought to treat it as such. So it's on the question of assurance. Now, I would say that most software products follow the faith-based assurance approach, which is to say, I have total faith in my team of crack engineers that they will produce. That is to say, you don't really have any assurance approach at all. You're just crossing your fingers and hoping that you can patch the software before something terribly bad happens. Or you can say, well, we can sort people bugs, so it'll be fine. And it's probably true, they will find the bugs, but you don't know who will find the bugs first. And it's quite likely that the people who want to steal the money or take the system down will find the bugs before the other people that send the report. That is not a great form of assurance for these systems working. So what's the alternative? The alternative is evidence-based assurance. We use evidence, and the same thing here. You want to look at you have evidence that the thing does what it's supposed to do. So in this case, what does that mean? Objective about the software artifacts. Right? This is not about the process. This is not like, I can't remember if it's ISO 9000 or 9001. Someone will know. There are sort of standard process. I'm talking about assurance about the objects that we run, the software that we actually produce at the end. So it doesn't matter, how it was made in a sense, so long as it produces what it is. And it should be objective, and it should be reviewable by any sufficiently expert third party. And that holds us to a standard. If you take that approach, it's not that you can't produce without producing evidence, but having to produce the evidence forces you to take an approach which produces high quality. So I think it's very important and asking our users to demand that of us. So then, of course, the development process itself does have to generate a little detail and talk about what does that mean, and then how are we doing that or approaching that within Cardano. So what does good evidence look like? Well, we use well-founded computer science techniques. What was there about 80 years of academic research in programming language design? There is vast amounts of good computer science that does not get used in everyday standard software because people think it's too slow, hard. They want to do just stuff quickly. But if we want to do things well and produce evidence about the code that we've written, there are actually lots of techniques out there that can generate about facts. So key things are specifications and formal specifications, not just like long documents with lots of words, but when we say formal specifications, we mean specification is mathematics, or a combination of prose and and mathematics. And the key idea of a formal specification is it says concisely what the system is if your specification is as big as your implementation. That doesn't help you with checking that it's right, because you can't fit either of those things in your head. And this is mathematical notation, like you've all got one in front of you. This is a, without any prose around it to explain what it does, but it's a precise, and we want to use, so that's the approach we want to take for many parts of our system where we want to generate evidence. So we want specifications about as many of the importance within the system. So then, so you've got a specification, and then you've got some code that runs, that is the real thing. And you want to be able to link those two together. So you want evidence that the implementation and the specification agree with each other in some kind of sense. The one is an implementation of the other, or there's different notions of exactly how they relate, but you want some evidence that you really sure and these two things are equivalent, or that one is an implementation of the other, implementation meets the specification. And there's two basic approaches to that. The gold standard, and that is great, but it's also still, even though we've made a lot of improvements over the years, it's still slower and more expensive than just which is testing evidence, and that is not as good. It's not as good as proof. It's not the gold standard. Right down there at the bottom. So the testing is a sort of lightweight method. It's much cheaper and quicker than the proof gold. But it's much higher quality than industry standard. So it's a compromise, but at least it's a compromise between perfect and pretty good, rather than a compromise between good and industry. It's a compromise on the right side. Okay, so that's the two basic ways, like gold standard and kind of lightweight methods, particularly testing. Later. So within Cardano, how do we approach this? So as people have discussed this morning, and Aglos talked about, we start with a lot of peer-reviewed research. That's in many places, in many areas of the system, and this includes things, of course, like Ouroboros, protocol design, but also game theory and incentives, and there's other areas that Aglos. So that's our starting point, some really great ideas, research papers. And then we have, as I said, we want to write these formal specifications in a concise mathematical style of what is actually going on. Having got some ideas from all these papers. And then we want to design our software, not just, there's a spec, and then we go and write the software and then try and, you have to software with that specification in mind, so that they can be compared later. It turns out from many years of people trying to do them totally separately and compare them at the end, it just doesn't work out. It's too hard to compare a implementation that was designed completely independently of its specification and try and compare them at the end. You have to have your spec. You can co-evolve your implementation and your specification, but they have to come together. Otherwise, they're just incomparable. And then at the end, we want evidence that links our implementation with our specification. And within Cardano, the track approach. Remember I said there was like the gold standard, and then there's a kind of the pretty good. And we're doing both. And we're doing those over different timescales. So we are doing the first, the light approach, and then we're following up with, in certain areas where it's particularly critical, we're following up with higher standards of evidence using more measures. I'll give examples a little bit later on. So just before we move on to, I want to go through in a bit more detail one particular example about the ledger layer, the ledger rules. But just before I do, also in general, and we see this problem quite concretely within IOHK, is that there's a massive gap actually between the output of academic computer science, what ends up it's sort of interestingly symbolized here, actually, within the room. So Aglos is sitting over here, and Phil and Manuel are sitting over there. And it's opposite of computers. You might think that those are very close together. But actually, being within that sphere myself, I know that those are, even they are quite a long way apart. You know, there's a that to a logician, they look at many mathematical proofs and they go, oh, I wouldn't do it that way. And the other side the same. They're not wrong, they're just different. And then if you imagine, right, they're that distance apart. Now, what about the engineers? They're like, you know, in the next street over there. There's the distance apart, like the language, the culture, what we focus on. It's surprisingly large gaps. And this is the problem we have throughout the entire history. So we can't just, and so IOHK funds lots and lots of research, as Charles was saying this morning, and Aglos was saying this morning. But you can't just write papers and then just chuck them to a bunch of engineers and say, right, go implement that. That does not work out. So what have we done to try and to bridge that gap? One of having helped IOHK with is to try and help bridge that gap by putting in place a team in between, people who can understand, you know, the needs of engineers and the low-level details, and also can understand, at least to some degree, can understand, you know, the papers that have been written. So Philip, who's sitting over there, is the head of our formal methods group, and that group is there exactly to bridge this gap. And this is not a new idea. This has been done for example, Microsoft Research. Microsoft introduced this entire new group to help them bridge the gap between, you know, their engineers in Redmond hacking out code all day and trying to, you know, smaller scale within IOHK. And so far, that seems to be working out. How we're doing this, you know, concretely for an important part of our system, which is the ledger rules. So the ledger layer is there that sits above the blockchain. What is allowed to go on the chain? What makes a valid ledger? You know, can you add this new transaction onto the end of this ledger? Is that valid or invalid? And there's lots of rules for that, because it's not just transactions, and you need to specify very clearly what those rules are. And then, and then, as I said, we have this whole chain of evidence that we want to. So, what is this chain of evidence? Over here for the top quality artwork. So we have as I said, you know, at the very high level, we've got specifications and implementations, and we want to link it, it's, you know, equivalent and some reasonable quality of evidence. This is not going to be the gold standard proof style evidence. It's going to be, you know, some test evidence that, in principle, third parties could repeat these checks. Over on the far side, I have Haskell, and then the next step across is a Haskell executable specification, and we need to produce evidence that these two things are linked. And then we've got the Haskell implementation, the real implementation, and again, there's a link between that and the Haskell executable specification. And you go into a bit more detail about each of these steps. But that's the big picture. We've got the specification document on one side, which is a PDF with lots of rules. On the far end, we've got the real implementation that really runs and operates the system. And in between, I'll come into a bit more detail. So specifications are not God-given. They don't just in point of enlightenment. They are in the way that the program's developed. You start by scribbling down something and you go, oh no, that's not right, let's do it again. And you share it with your colleagues and you think and you go round and round. And then you halfway through, like, okay, review and talking to other people, and it goes around and around and iterates and iterates. So this is still very much an iterative, incremental process of producing a specification. But it produces this formal mathematical style. I'm not going to go into the details of exactly what's on this slide. It doesn't matter. The point is, you've done enough iterations and you've done enough rounds of review, and you say, okay, this is pretty good. We agree this is actually what our specification is. I like these ones because it's rules for UTXO and UTXO with witnesses, and they fit on one slide, and that is actually very nice. If you want me to read off like what things mean, for example, in Figure 10, this is the rule that says that you need to have witnesses for a transaction to be valid. That each input has to sign, have a signature for each input, corresponding to each input, that signs the entire transaction body. So someone who did like first year mathematics and had read this a couple of times, this off English language in their heads and go, yeah, that sounds right to me. So let's read it off. So it says, for all, yeah, that sounds right to me. So let's read it off. So it says, for all I in transaction inputs, so that's for each input in the transaction, lists a verification key and signature in the set of witnesses, such that we can verify on the signature the same transaction that signature and that verification key, those verify with the transaction body. So and the UTX responds or equals the hash of the verification key. So that is exactly what you need for. It has to correspond to the hash of the verification key corresponds to the address, and the signature and verification key together can be used to verify with the transaction body. So that's in one line what witnesses are. And what's really good about that is it's really compact. This is so small that you can fit it in your head, and multiple people can sit who are with different backgrounds and experiences on the problem can fit and say, yes, that is actually what we want. It's no good if people don't understand these things, right? Then it's just like squiggles on a piece of paper. It has to be in a language, precise language, in a language that enough people understand, experts at least, and that is a challenge, but enough people can understand it and say, yes, those actually are, not only are they self-consistent rules, but they are sensible rules. Those are the rules that in fact we want. So it's express that when we choose the language in which we express these rules, that it's a language that people can understand. Right? It's no good if we write it in some awesome theorem prover that only 3 people can read. Charles and Aglos over on the far end there saying, yes, these are the ledger rules that we want. Not only are they self-consistent and make sense, are the rules that in fact we want to deploy on the chain. And they can read it and they can understand it. So that's, okay, we've got our... So next one is the link between the specification document and the executable specification. The executable specification is very important because it's what we will use later for testing. So this is going, this style of rule on paper into something that actually runs. And so this is an important transition. And we do this by writing them in various styles, but different languages. The one is, well, here we go. The top one is the one that I showed you a second ago. Well, actually, it's the first of the 2 rules I showed you earlier. So this is the main UTXO rule with the Haskell executable specification, and they are supposed to be equivalent. But one of them we can actually run, and one is just the other one is more for other people. So this step requires people to read both and say that yes, those are. So this step requires people to read both and say that yes, those are the same as each other. And they sound, but they're written in such a way that they really correspond. This is only a few pages, so they match up. So each of these things on the, I'm not going to go. It doesn't matter. We don't have enough time to go into all the details of like every single bit here. But the key point is how they correspond. So each of the top predicate, and that corresponds to the Haskell code. So if you look at that, so transaction ins is a subset of the domain of the UTXO. Okay, so in the Haskell code it says inputs is a subset of. Okay, that's equivalent to the mathematical subset operator is equivalent to DOM of the UTXO. That's nice. So those correspond quite closely. That's a additional detail that's in our executable version that says if it fails, why did it fail? Which the mathematical version doesn't say. It just says it must satisfy all of these things, otherwise it's not. We can make sure that we generate ledgers that cause each individual failure to happen, and so it's useful to be able to classify those failures. It's the top corresponds to one of the predicates in the in-house code. There's a little bit of translation, but they're really pretty close to each other, as I think you can see. So the ones above the line were predicates, things that must be true. The thing below the line is a state transition. It says, if you are in this starting state, so long as all the predicates are true, then move to the these really very closely. Particularly closely because we're using Unicode Haskell operators to correspond to the special operators in mathematics. So this process of checking that these two things are the same is doable. The reasonable degree of reliability. I mean, some humans have to do it, but it's doing any repeat the process. That's the hairy one and evaluated. And we want to check that the real implementation, which has lots of detail and property specification, but it's an executable specification. And this we now do using testing. So the people in the middle there are saying, yes, the tests pass. And talk about what tests are. So as follows. We have, at the top, we've got the executable specification. At the bottom, we have the real implementation. And these we're modeling here as functions. Of course, the real. And what we need to be able to do is say, for any state of the real implementation, we have an abstraction function that takes that state of the executable specification. And so long as we can do that, then if we generate thousands, hundreds of thousands of transitions in the real and so what does that mean in this case? It means ledgers, right? If you take generate an example ledger and you feed it to the executable version, the executable spec, and you feed the same ledger, the real one, and starting in an equivalent state, they should end up in equivalent state. And you can tell they're equivalent by applying the abstraction function and checking they're equal. So what that's telling you is that for that would be proof, but for many, many, many correct and incorrect ledgers, if you feed the same one to the real implementation and the spec, they give the same results. They end up in a state which is equivalent. So that's not proof. That's not for all possible, not all possible ledgers, but by testing with generators that produce, we can generate as many ledgers as we like. So long as we get good coverage, then that kind of testing is really pretty good, and that really finds the bugs. And this technique has been used for decades. This is a well-established technique, and it's very effective in finding bugs. The proof is really good. So that's the story with the testing. Beyond that, I'm not going to go on too much longer now. Testing, as I said, we have in certain cases where it's really important, we are using more than just lightweight and methods and testing. So in particular, there's 4 examples at least that we're doing this with. For the Cardano wallet, which we released at the beginning of this year, following a formal spec approach from the spec published back in spring, we are now following up that work by formalizing the spec that we did on paper in the Koch theorem prover, and proving the properties that we only tested previously. So that's going along the same path that we did previously, but now to a higher standard. And so far, what's really nice about that is that we've not found any new bugs. We did find bugs when we ran them through the tests, when we did the quick check testing approach, the same technique as I showed a second ago. That technique did discover bugs in our implementation. But so far, the formal proof has not found any new ones. And that's actually a good thing. that shows actually how effective the testing was. But the proof is, of course, a higher standard of evidence. So that is something that we're following up with. And we're going to do the same thing with the ledger rules. We haven't yet. That is on our list. Now, in addition, we have people working on formal approaches to the development of Ouroboros, new versions of Ouroboros. We are doing a more formal approach. And the way we're doing that is by re-expressing Ouroboros in terms of a process calculus, and then formalize this in the ISM prover, and we will prove properties about that, and we'll prove relationships between the abstract version and more concrete versions. So again, it's trying to link level. In the other track earlier was talking about this last one about formalizing Plutus core in Agda and properties about Plutus core using Agda. In particular, progress, preservation, decidability. I'm not going to go into the details there, but again, Agda is another exactly theorem prover. In this case, are used sort of as a theorem prover, and this again gives you a very high standard of evidence, even better than testing. So, in conclusion, before we trust or evidence, and additionally, we are trying to follow through on that. And I think it's not just of us, but of everybody else. Hold our feet to the fire and everyone else's and say, show me the evidence. I want to see that your system does what you think. And we are trying to do just that. Thanks very much. Questions?
No, you're okay. Thank you. All right. Hello, hello, test. Check.
Thank you, Duncan. Right. Finally, for closing remarks, we have Rebecca Valentine. She has been with us for quite some time. Our first member. Are you not? First engineer? Yeah, I think you are. She joined us in 2016. She is a type theorist and functional programmer who occasionally dabbles in linguistic theory. She's used methods, especially dependent types and novel type systems, for building provably correct software. She has implemented a number of pure functional programming languages and delimited wow. Continuations. That's, I don't know. Okay. She is also an documentation of software, very important, especially literate documentation where possible. What do you mean by literate document? Just, it makes sense.
Better than illiterate.
Very nice. Rebecca.
Limited continuations are a real thing.
Are they?
Yeah.
Sorry.
Okay. I'm going to keep this relatively short because we've been here quite a while today.
I'm sorry. This is what has happened. Can I have this box now? I'm so sorry. For now.
Hello?
Yeah.
Cool. Awesome.
It's the last time I'm doing it.
So, a lot of work from some Marlowe teams on fleshing out the Cardano ecosystem. I would like to look towards the future. I would like to ask, what is the significance of this moment in time in terms of writing history books on the history of programming? What will be the import of this work? And I think if we've done our jobs well, it's going to be the seed for blockchains, but software in general. So right now, the current cost of an error is relatively small. You do have bugs which do often. For instance, if your rocket blows up, that will cost you a lot, but that happens pretty rarely. The costs of these bugs are spread over time, and so we're space have more things rather than big things. However, additionally, the organizations that have large, costly bugs. So the DAO did not have insurance. I mean, who was going to insure it? It was expensive compared to the amount of code involved. It was dozens of lines, not hundreds of millions of lines. And so the costs are getting larger and immediate. This work aims to ameliorate this problem by getting us ways to write better software, better languages, formal methods, machine verification. But the older academia, it's not NASA, it's smart contract writers, all smart contract writers. And so what that means is many orders of magnitude more people will be using these techniques than the really technique. And more people will be exposed to these techniques than ever before. What are the implications of this? Again, not for Cardano, but for programming more broadly. To higher software quality overall, partially by using them directly, but also because as people who use the technique on a regular basis, it changes how you think about writing software. Your thoughts themselves become more rigorous, and it changes the thoughts that you have, the kinds of thoughts you can have. Second, as there are more, again, partially directly by demand, but also because you'll just have more people exploring the possible, because more eyeballs are looking for them. And thirdly, there will be more incentives to educate people. It's been said that you sort of need a PhD to use the types to your languages programs. This is sort of no longer true, partially because YouTube has lots of great courses that people have taught. Also, we have books like Type-Driven Development, which if you go hackerspace world, people are reading type-driven development and having little study groups, and it's just average people. The work today will drive even more changes like this. You'll get popular books on but on theorem proofing and the tools associated with it. You will also get more blog posts, more tutorials, more online courses, MOOCs on all of these things. And you'll get a web for experiments with them. You can go to Replit right now and run Haskell, which is pretty cool. But what's next for Replit? Will it be Agda and Coq? Who knows? But I think it's inevitable. And so I would like to thank the Plutus and Marlowe teams for planting the seeds of this change and for helping to bring about this very interesting future. I would like to invite all of you to build, and I can't wait to see what you build with Cardano. Thank you.
Thank you very much, everyone.